start by thanking the organizers for inviting me to come give this talk at this very good conference, so I greatly appreciate that. This program is one that I started almost a year ago at IARPA. IARPA is very similar to DARPA in the United States. We just focus on the needs of the intelligence community versus the defense community. In 2010, I was at DARPA, and I ran the DARPA exascale studies. And the studies were focused on, could we do an exascale system using 20 megawatts of power? At the time, that seemed like an outrageous challenge. The numbers that people were projecting were up to a gigawatt, so clearly that would be unacceptable in any computing center. In the United States, 1 megawatt costs $1 million, so 20 megawatts is $20 million a year in power, so anything higher than that really exceeds what most facilities could provide. The interesting thing about it, though, is that part of the study concluded that one of the problems was data. But the data problem that we were focusing on was the energy cost. You were dominated by moving data around, and it consumed a lot of energy, so that's where your 20 megawatts were going. At the time, we didn't think about it, but the problem goes way beyond energy required to move the data. It's the problem of moving the data itself. The particular problems we were probably focused on were basically physics-based modeling, where random sparse data isn't quite the same problem. So I started this program at IARPA to attack this data analytics problem that we're facing today and tomorrow. The basic problem is that for today's systems, most of them are CPU focused. You heard it yesterday. The keynote speaker said that the future is specialization coming in with new specialized processors. But that doesn't really solve the problem, because if I can't get the data to the processor efficiently, then I can't get the performance out of it. It works very well when I can preload a lot of data to the CPU or whatever it is and operate it on as many times as possible. But that's not what we have in the data analytics arena. So the program overview is we're looking to turn the analytics into near real time versus hours, days, months, depending on the problem. What we want to do in this program is create a new generation of architectures. Just to be really clear, this program only develops the designs. It's not developing the architectures. That cost would exceed what I have in the budget. But as I said, we're developing full system architectures. This is not do a better CPU, do a better memory, do a better network. It's the whole system, because you're moving the data from everywhere to wherever you're processing and wherever you're storing. It's constantly moving data all over the place. These designs are being held to some standards called the target metrics. They were in the BAA. If you're interested in them, I have one set included in the talk here. Performers are held to very high standards in IARPA programs. Everything they do is independently tested by groups. In this particular case, it comes from 3 DOE laboratories. The designs are all developed, but then modeled using a mod sim environment. In this particular case here, we use SST, which comes from Sandia National Laboratory. There are 2 phases in this program. Phase 1 is 18 months. We're about halfway through that right now. At the end of phase 1, what they're supposed to do is develop a behavioral model for their system. This basically models how the system will behave when you actually build it one day. All right? And phase 2 is doing RTL designs, which is really the next step before you actually start developing hardware. And that also is modeled. So what is the problem here? Well, as Neil said in his talk, Moore's law, Dennard scaling, is no longer providing the performance that we need in the systems. Okay? We have this explosion of data. Everybody's quite aware of that. Everything you use in Facebook, Twitter, whatever you want, is exploding in terms of data volume. That's causing a serious problem. And what we want is to be able to have what is called actionable information, actionable knowledge. I mean, you know, you've got a lot of data, you want to learn something from the data, you want to learn it as quickly as you can. In some cases, quickness may not matter, but in other cases, it is. If you're in a surveillance situation, looking at a scene, you'd like to understand what's happening now, not 2 weeks later after some incident occurred. Probably most of you are quite aware of this, but most data analytics problems can be expressed in terms of graphs. So really, at the end of the day, what you're doing is graph operations on these problems. But these graphs can be absolutely huge, as this chart shows here. This is actually data from 2013, so it's 10 years old. And at the time, they were predicting that the social networking was generate a graph with 1 billion vertices and 100 billion edges. I suspect if we were to look at this data today, you'd see it's massively larger than that. Now, all data analytics, though, is more than just graph analytics. It comes down to a whole host of different algorithms that must be included in there. So the challenge to the performers under the Agile program is not to just do graph analytics fast, but to do all these other operations as necessary. So it's not just a graph analytics system. All right, so as I said, we're creating these designs which are validated using a modeling and simulation environment called SST. If you haven't heard about it before, it is at Sandia National Laboratory. Just Google SST Sandia. If you do Google just SST, you'll find a whole bunch of things. But if you Google Sandia, you'll find it. This is the important part right here. The data is assumed to be sparse, unstructured, heterogeneous. The computations have minimal locality and poor data reuse. So I go to all the trouble to bring the data to some processor. I use it one time, and then I'm done with it. This is not the way dense linear algebra works. Dense linear algebra works by bringing a block of data into your cache and operating it on as many times as you can, which typically is fairly large. In this particular case here, I bring the data into whatever that memory is, or cache or whatever, and I use it once, and then I'm done with it. That's incredibly poor locality. This results in extreme parallelism, and often the computations are data-driven. I don't know what's going to happen until I get the data, and the data tells me what I do next, which is completely different from where we are today. Today, everything is driven by whatever piece of code I wrote, and it operates on whatever data is there, and it's not very highly data-dependent. So as I said, the outcome is these full system designs. At the very end of the program is the RTL-based design. A key element of this program is the fact that you can't just do a design, you have to talk about the runtime. The runtime is the software that sits on top of the hardware that basically controls what happens in the hardware itself. For that to be efficient, in this particular case, you need to have hardware feed into the runtime to tell it what it's doing so it can monitor and change things accordingly. Another key element here is that the designs at the end of the program have to be validated, meaning they have to work correctly. The assumption here is that somebody's going to take these designs and either continue working on them or build a system based on these designs, and you'd like to know that it's been validated. I also already mentioned the fact that all of these designs are independently tested by 3 DOE labs that are under contract to evaluate them. They are independent. They're not cross-performers or anything like that. So they give me an independent assessment of what they think. The whole thing is driven by 4 workflows. I've listed them here. The first 2 basically work on knowledge graphs. The third one is doing clustering of data sequences and other similar operations. And the fourth is influence maximization. We provided these codes to the performers with the appropriate data sets. They can implement the workflows however they want to. because if you change the way processing and data movement takes place, that impacts the algorithms that you would use. So we cannot tell them, stick to whatever we gave you, because that would not give them the best performance, which creates quite a bit of challenges, of course. Because then in turn, we have to validate that what they did was correct and they didn't take any shortcuts. There's a favorite expression, which is trust but verify. And unfortunately, my director is very big on the verify part. So I can't just say, gee, I've known you a long time, I trust you. That won't work. So I have to be independent. So the problem we have is that today's computers are not designed for these type of operations. Today's computers, which are very fast, are designed basically for large-scale physics simulation. Yes, in the last, let's be generous, 10 years, we can start talking about machine learning and other operations, but the systems that are used for that are basically a traditional high-performance computer. So I just have this one example here. There are lots of these, but I don't have a lot of time in this talk. This benchmark here, called HPCG, is doing conjugate gradient on a very large, sparse linear system. It's done by the same group that does HPL. HPL, you might not be familiar with that term, but it's basically the LinPack benchmark, where you allow the size of the matrix to go as large as you want, and you're measuring what the performance is. So that's called the top 500. Every year, twice a year, the results are collected for the top 500, and that gives us what the fastest computer is. It's the fastest computer for HPL. It is not the fastest computer for these type of problems. As I said before, these systems are designed for large-scale physics simulation, not for this large sparse problem. So HPCG here is a sparse problem. It's a very large, sparse linear system. Basically, if you're not familiar with conjugate gradient, I imagine many of you are, you're basically doing a large sparse matrix times the dense vector. And that's a fundamental problem. And then there's some collective operations, too, which kill the performance. So right now, and these results were from May of 2023 at the recent ISC conference. The #1 system is Fugaku, which is a very good computer in Japan. On the top 500, they're #2, so it is a very fast computer. They're #1 on HPCG. What's interesting is this number right here in the far right-hand column. This is showing you efficiency. This is just a ratio of the performance it received versus the total performance it could have delivered, okay? And so in this particular case, Fugaku, very good computer, is 3.6% efficient. That means 95% or more of the resources are not utilized efficiently in this operation here. That's a lot of waste of a very expensive piece of hardware. #2 is Frontier, which is the fastest computer based on LinPack, and they're doing fantastic at 1.2%. So there's your first exascale system, efficiency 1.2%. That means we paid $1 billion for a computer, and we're not getting good use out of it. The reality is they are getting good use out of it because it was designed for the problems that are being attacked at the DOE laboratories. So I'm not trying to be critical of it. I'm just trying to point out the fact that the system is not designed well for this large sparse problem. Okay, so one of the differences here is not just the data movement problem itself, but the actual characteristics. So what we want, as I said before, is we want near real-time solution. Okay? We're going to have streaming data. Streaming data. Data is coming in from an external source. It's a sensor, it's a camera, whatever. You know, maybe it's just looking at a current feed on Twitter, whatever. Data is coming in, it's represented by a graph. That means that the graph that's already stored in the computer is constantly changing. So it's not static. And therein lies one of the problems. A traditional way to deal with large sparse problems on a computer is to cluster the data so that when you operate on the data, you're operating on the data within a cluster and not spending a lot of time going outside of your cluster. That is not very possible when streaming data is occurring and you're changing the data all over the place, so that's a bit of a problem. As I mentioned before, we have extremely fine-grained data movement. You know, when you do an operation, you need a couple of words, you do something to it, as I said before, I'm done. I don't need it again. And so I go off and get data someplace else because, again, the streaming data is constantly changing the graph itself. I already mentioned the fact that it has poor data locality. Okay, the key to this program is that everything is driven by a co-design process. What that means is you don't let the hardware engineers go sit in a corner someplace and fantasize on how they think something should operate and then give you a design set here. And then the software people have to deal with the fact that the hardware is not compatible with their software and such. Also, the problem is the system itself wasn't really designed, driven by a set of problems. Traditionally, hardware engineers do have a set of problems that they deal with, but it's very low-level kernels. Okay? So in this particular case, as you've seen, we have 4 workflows that they have to deal with. These are actually, relatively speaking, large codes. They're broken into kernels, so they're more easily managed. The co-design process, basically what one does is you work on a design, you see how it behaves on your workflows or kernel or whatever you're looking at, and then you change your design and you just continue to loop around and around. You also could analyze the workflow and you could say, I think this is the type of design that I need, and so you would change that element, you incorporate it in the design, test it, and around we go. It's a very important part of the program. And there are basically 3 aspects to the co-design process that we focus on. Number 1 is performance. As I said, everybody has to achieve these target metric values that are in the solicitation. Productivity is very important. One of the problems with dealing with these large, sparse problems is that it makes the codes very complicated because you're trying to optimize the efficient movement of the data in the system. And that makes the complexity of the program even greater. And so productivity is a significant issue. I am not here to say that we're going to measure productivity. Measuring productivity, if you've ever looked into it, is a very nebulous space. You can't really define what productivity is. You know it when you have it, but to actually put metrics on it is a challenge. Efficiency. The efficiency is very important. It covers efficient use of resources. So I would have said that the Fugaku and Frontier system are not very efficient because you have a very small percentage of efficiency. But efficiency also here is in reference in the fact that we don't want people to play games with these metrics. You know, you're doing a software simulation of the execution of the program. You could let that sucker run forever, put as many resources in it as you want, and that'll give you incrementally a little bit better performance every time. And so that sounds nice, but that's not nice because nobody's going to want to have a monster-sized system. The assumption here is that we're talking about dozens of cabinets for the particular problems. The actual solicitation said you had to scale from desk side to data center size systems. The actual size is driven by the problems that we've given them. Okay, so in summary, what we have are 3 benchmarks, which I really haven't spent any time talking about. Then there's the 4 workflows, and they're focused on the streaming data analytics problem. That's what drives the program. So I want to talk a little bit about some of the workflows. I won't go into a lot of detail on this, but otherwise we'll be here a long time. The first one is a knowledge graph. And basically there are 3 kernels inside of the knowledge workflow that we're looking at. The first one is looking for indirect connections between vertices. The second is identifying new entities within the graph itself. And the third is finding new relationships. So that represents 3 different kernels that are in the workflow itself. So this is what the flow computational flow graph looks like for this workflow. there are a total of 5 kernels. The first kernel basically reads in the data, forms the appropriate operations necessary to do the graph later on, because you're reading in just raw data, okay? The second is forming a graph neural network, which is used for the 3 kernels that I mentioned a second ago. The 5th kernel is this one right here, and this particular one is where we are streaming in data. Up here in the top, kernel 1 was you're reading it from a file. Here, I'm streaming the data in, so I have to update the GNN. Otherwise, I can't really apply it to these 3 kernels right here. Okay? So that's the layout for workflow 1. I'm going to skip this, but it's in there. So this is important to mention here. So we developed these workflows. They were developed at Pacific Northwest National Lab in Washington State, United States. They were written to use libtorch and a package called SHAD that was developed at PNNL. These are reference codes. These are not optimized. They're not intended to be optimized. They're intended to show the performers what is expected so that they can understand it and rewrite it for their system, okay? So this is a different way of looking at the flow of the, but the key thing here, these are just reference codes written in libtorch and SHAD, and I think they're all written in C++. And so here's the target metric table that came out of the BAA, the solicitation. You have the 5 kernels that I've listed right here. This is what we thought the time was at the time we released the solicitation. We actually have new numbers here. I just received them, so I haven't had time to incorporate them into the tables yet. This column here is where we thought we wanted to be able to go. This is based on talking to people who actually use the workflows, or these type of operations, maybe not just the workflows, and want to know how fast something needed to be to satisfy them. Each performer is going to provide us with their own estimated values right here. That is something that has or will occur in the very near future. So we're not holding them to a standard that was basically randomly set by guessing. The 4th workflow is kind of interesting. They're basically taking 4 or 5 networks and forming one network out of it, okay? And then on that combined network, you're doing influence maximization, which basically you're looking for K nodes that have the greatest activation on other nodes in the network. So you're looking for the trend setters. You know, if you were in sales, you'd want to know what it is that drove that. If you're looking for bad people, you'd like to know who the bad people are influencing. And so this is the task graph for workflow 4. It's actually not complete, but it's similar to the other one in that, and then by the way, it says select coffee market. It's a particular problem that we gave to the performers. It had to do with finding coffee markets. You could put anything you want up there. So the first you bring in the data, you do the influence maximization, and then you eliminate those nodes and update the graph itself. This influence maximization is really an interesting topic. If you Google it, you'll find some very interesting papers on it. Okay, so what are the technical approaches that people are going to use? They vary tremendously. And a system today, it's really tightly integrated, and there are boundaries at the same time. So that creates a problem. In the case of the agile systems, we were looking for more tightly integrated to remove the barriers between the components, basically, because those barriers just slow you down. Today, a system is basically pre-programmed sequential process. You write a code. As I said, it doesn't really operate on the data. Sure, if I'm doing an iterative method, I might wait for convergence till that's achieved. But the algorithm I would execute is the same regardless of what the data is. In the case of the agile systems, we're assuming it's data-driven. So that means that things are constantly changing. Parallelism is constantly exploding. In the case of a system today, you're basically always monitoring your local memory. You know, what's in my cache, what's in that local DRAM, that's what you're paying attention to. And that's fine. There's nothing wrong with that. That's what you should do. In the case of the agile systems, what they're mostly doing is looking at distributed memory management and not trying to deal with caches. Caches don't do well with this sparse problem. The problem with a cache, in case you're unaware, is that when I load into a cache, I load what is called a cache line, which can be anything from 4 to 8 or more words of data. If all I needed was 1 word of data to do my operation, I loaded a lot of data that I didn't need into the cache. And that's a waste of time and energy. Okay? Global namespace is important. Right now, it's all local. When you process data in a parallel environment today, you're in a distributed memory environment. And what that means is I control my data on my processor, my node, whatever you have. And if I want somebody else's data, I have to send a command over there and says, give me this data. And locally, it determines where that data is and then sends it back to you. In the case of a global namespace, I can reference any data all over this place. As I said before, runtime is incredibly important. In this particular case, we have a dynamic runtime, which means it is adjusting based on what is happening within the system. All right, so we funded 6 performers. AMD, Intel, and Qualcomm are the 3 industrial performers that were funded. And the university teams was Georgia Tech, Indiana University, and the University of Chicago. So we have a mixture of industrial and versus academics, which is good. It's interesting because I find that the industrial teams are a little bit less risky. They're a little bit driven a little bit more by what is available within their product line. And they're looking towards how do I get this into the product line going forward into the future. Academics, on the other side, they don't worry about a product, and they are freer to think. And sometimes their freedom to think produces results that are not as realistic. So it's a good mixture to have. I can't talk about all 6 in the time that I have, which I have no idea what it is. So I wanted to talk about 3 of them. When we wrote the solicitation, we were very clear in saying that there was going to be open discussion of the various projects. Openness means a little different to the academic versus the industrial. And the industry teams are willing to talk about it, but they view it as proprietary efforts, and they're less willing to talk about it in an open environment. Academics are always happy to talk about it. They're going to write a paper on it. They're a little cautious because they don't want to talk about it until they feel the research is proven itself. So they too are resistant. So let me first talk about AMD. This is a really interesting problem. Basically, what AMD is going to say is, well, we're going to compute everywhere. We're going to have computing at the memory, at the node, maybe in the network switch, in the storage. We're going to put computing everywhere. And so what we're going to do, they're going to do, is they're going to do the processing based on where the data is located, as much as you can, which is not realistic to say I can do all my data computations where the data is located, because I could have the required data in 2 different memory locations, 2 different nodes, and obviously, I have to bring some data someplace to do that operation. But all the same, it's a very nice concept. It requires hardware support. It also requires software, because what you don't want is a system that says you have to tailor your application to the hardware that you have. You don't want to do that. And the reason you don't want to do that is because whoever did that then has to change their code completely when you move it to a different platform. Everybody wants portability to some extent, okay? And so the way you deal with that, of course, is in libraries or the runtime environment itself, which monitors where the operations need to take place and does the appropriate thing. So it's a very big challenge to do this efficiently and meet these problems. The second one is by Georgia Tech. Vivek Sarkar is the PI, and Peter Kogi is also on this. They're basically doing moving the compute to where the data is. And they're doing that through active messages, and it allows them to when they hit a point where they don't have the data, they move that thread to where the data is located and do the processing there. And you could get this ping pong effect going on because it's going to constantly move. There's 3 different approaches here. One is the actor message. Over here, this is talking about atomic operations. Atomic operation is a simple operation on one word of data. You might increment it. You might check to see what the value is and swap it with something else. Something that's focused on a single data element. And the last one is this one here. This is where we're actually moving the thread with the data to the location. All 3 of these have hardware support. The problem with active messages today, and it's been around for at least 30 years, there wasn't hardware support for it. It was all done in software. So you lost the efficiency of moving the compute around. And the last is the Indiana. It would really take quite a few slides to fully describe this, so hopefully I won't make a mess out of it. The basic idea is they developed this Fontan. It's an incredibly small piece of logic. And on a chip, they're going to put somewhere between 20 and 40,000 of these things, so you can imagine they're very small. They haven't decided exactly because they're still in the design phase. The Fontan, way to think about it is this triangle that I'm showing up here. You basically can receive data from any one of the 3 sides, or I can send data out any one of the 3 sides. So that gives me this switch in the middle that makes the determination. There's also a ability to do computation in here. So you send a tag and it says, this is what I want to do the data, and then that tag tells what logic needs to be operated on the data. Each Fontan has either a network switch that allows me to hop across Fontans, or it has a floating point unit. All of these operations in here, I think, are integer operations, okay, or bit operations. And every now and then you need to do a floating point operation. You can take 6 of those and spin them together, and you get this cluster of them right here. So 6 share 1 floating point unit, 6 share 1 local network access. Okay? And then you take those clusters and you build up the chip. There's other things on the chip, which is why they don't know exactly how many they're going to put on there at this point in time. And so what's happening here is you're moving around what they call an operon. I showed you a picture up here. You could think of it as an active message on steroids. You're basically moving off an operon between Fontans. It changes it. It does an operation. It moves it around. There's a variety of operations that it does. Incredibly lightweight computation. OK, so I mentioned this already. The key here is that everything is being modeled and simulated. It's not just a paper design. That would never pass this test at IARPA. And so that modeling is done with, as I said, SST. That's for the software implementation, the behavioral design. And FireSim is doing RTL emulation. So that's going to give you faster results. But you really need to do the behavioral modeling before you do the RTL. You don't jump to the RTL. There are quite a few challenges associated with this. As I've already said, we have some fairly decent size workflows and data sets. We've tried to size them so they were not outrageous. We are pushing the limits on what SST is capable of doing. It is not traditionally used for full system modeling. They usually do it in terms of modeling a component or a simple node in the system. Here we're doing a full system modeling on real applications, not toys. So that's important. They have to be able to demonstrate the target metric values. That's critical. As I said, we're doing this full system modeling, which takes a lot of effort. Runtime is a critical part of this effort. The runtime requires the hardware when you want to operate the hardware. So how do you develop the runtime if you don't have the hardware? Well, you can develop the runtime in software, but it has to sit on top of a layer that is software emulating the hardware. And so that's fine. That's the right way to do it. And that allows you to test the runtime without worrying about what's going on in a design. Because the design itself could have errors, and you need a way to know what works right and what does not work right. This is a very important one here, reasonable amount of time. You know, the way the program is structured is they have to have their model of the full system completed by the 16th month in phase 1, which is 18 months long. I have 6 projects that have to be all evaluated in a little over 2 months. So if the modeling simulation takes months to complete, we got a real problem here. So the way to deal with that, of course, is to change the size of some of the data sets as necessary, but also to get the teams to submit their designs or pieces of their designs much earlier so we don't have to do a full evaluation. We're going to verify the design and evaluate security. I didn't have really time to talk about this, but an important element in this program is security. They are designing systems that support multi-tenancy. What that means is that if I'm on the system accessing a graph, somebody else could be on the system accessing the same graph. I could update the graph, and so we have to do that in a manner in which it doesn't mess up the second person in terms of how they're using the data. The other aspect is we want to protect various elements within the graph so that I can read what I'm supposed to read and you can't read what you're supposed to not read. Security impacts performance, but it's an essential part of the overall effort. They will be tested on their target metrics with security basically turned off. But you can't add in security. You can't add in hardware security after the design is complete. You can layer software on top of it if you want, but the software needs to have support in the hardware for security. Okay, so we're trying to be inspirational when we started talking about this program. And so what I want people to understand is that we're really looking for people who are going to make a significant change in data-centric computing, much like it has been done in the past. These are some of my heroes up here. Thomas Flowers did the Colossus system here in UK. To be honest, I had a different person up there until I came to the UK, but I'm trying to be culturally sensitive. But you just can't imagine how hard it was, seriously, because when you start looking at the history of computing, there's a lot of people who said, oh, I did the first computer. Right? Oh, I did the first computer. And it is hard to pick who it is. Colossus is a cool system, though.
You should get 50 minutes with the other guy.
Okay, so I am almost done here. So basically I want to mention that what we're trying to do is generate this new design of systems that deal with data-intensive problems, because the systems today are not capable of doing it. Yes, the systems of today will do whatever you tell them to do, right? I mean, it's a computer, it's programmable, I can write C++, I can do whatever I want, basically. But what I want is larger data problems, and I want it faster. And what I've shown through one example, that these systems are not efficient, so getting it faster is not very reasonable. Okay? And we'd like to think of this as looking at what we call a clean slate. Realistically, you know, there's 60 years of investment in computers. We're not going to all of a sudden discover a fantastically new way of dealing with it. What we are looking for here is a better way to move the data around. And that's what the program really comes down to. So, thank you.
Thank you so much, Bill Harrod.